Okay, let's start by finding the domain of some different functions. The domain is all of the possible x values. If you're ever asked to find the range, that's the possible y values or possible output values. Okay, so really these should have little arrows on them to show they go up infinitely. This one is supposed to just start there, so that's not an arrow, that's just a point, but it should have an arrow there. Okay, all right, so looking at the possible x values, this one stretches left and right forever. It's going to get narrower, it's going to get closer and closer to going straight up and down. It's going to kind of flatten out so it looks like it's pointing straight up on both sides, but it's actually going to be widening forever as you go up. So that means that the domain is unlimited. This is going to stretch left and right forever. So I could plug in anything I want for x. I could plug in 1,000,000 and I would get a y value out. I could go 1,000,000 to the right on the x and 1,000,000 to the left, and I could go more than that. So the domain here is all real numbers. Okay, so the way I'm going to write that, you can always write out all real numbers. The symbol for it, if you have an uppercase R, I call it a fancy uppercase R because it's got that little part on the left, okay? And that just means all real numbers. Okay, so just looking at it algebraically, yeah, you can plug in anything in for x and you'll get a y value out, whether it's positive or negative, okay? Same thing here. So this is going to go left and right forever. It looks kind of like it's getting pretty steep on both ends, but it's going to stretch out very slowly forever on both sides. So it has no limits how far left and right this stretches. That means my domain, again, is all real numbers. Okay? And you can think about this again. You can plug in anything for x. There's no limitations there. Okay? The domain here is also going to be unlimited. So just looking at the graph, you can see the stretches right and left forever. That dot's supposed to be filled in, kind of the same with all these. So there's no missing x values, and it goes left and right forever. So the domain is all real numbers, okay? And you can plug in anything you want for x here, and you'll get a real y out. So you can plug positives and negatives. If you plug a negative in, that's okay. The cube root of -8 is -2, right? Since that index is odd, it's not limited, okay? Now, when I've got a square root, that changes. So just looking at the graph, I'm thinking all of the x values, well, it goes to the right forever, but it doesn't go to the left forever. That's the end of the road, okay? So it's a little hard to see on this graph, but that's supposed to be the point, -2, 0. So it goes to the right from -2. So my x values, I could have an x that's -2 or anything bigger than that, right? So that is my domain. And another way to think about that, hey, I've got an even index here, and that means that the radicand can't be negative. So that means the radicand is less than, or it's more than, or greater than or equal to 0. Sorry. So my radicand, that's this part. So x plus 2 is going to be greater or equal to 0. And that means when you solve this, that's my domain. And I'm seeing now that I messed up there. That goes from -2 to positive infinity, right? So I should have had my negative there. So the domain is x is greater or equal to -2. Okay. So it is limited when there's a square root. Just whatever the radical is has to be 0 or positive. Okay. All right. So looking at this next example, this also has a limitation. I don't have a graph here because we haven't graphed rational functions yet. We will later. But for now, we don't need a graph. We can just think, well, what can I plug in for x? Well, you can plug in a whole lot of different things. We could plug in 1,000,000. We could plug in -1,000,000. But there is something that we can't plug in because the denominator can't equal 0, right? Because you can't divide something by 0. You can't take 2 and put it into 0 piles. It doesn't work. So my denominator cannot equal, can't equal 0. So whatever's down there, I just say, okay, x minus 3 cannot equal 0. And then if I'm isolating x, I would just treat it like an equation. I'd add 3 to both sides. this is what x can't equals. That's what would give me a 0 denominator. So the most concise way, we don't want to make a list because it's an infinitely long list, but there is one thing that does not work for the domain. X cannot equal 3, okay? So for radicals, the radicand has to be positive or 0 if it's an even index. And then if you've got a fraction, the denominator can't equal 0. So watch out for that as well, okay? All right, those are really the two limits that we have to watch out for domains at this time, okay? Now we've got some function notation. So we're going to do some function operations, starting with adding and subtracting functions together. So f plus g of x, that's how I'd say this out loud. That just means f of x plus g of x. Okay? And so up above, I'm told what f of x and g of x are, so then I'm just going to substitute those in. So f of x is 5 root x. G of x is negative 8 root x. Okay? And then I want to see if I can simplify this. Well, these are like terms, right? I got 5 of those minus 8 of those. That means I'm going to end up with negative 3 of those being root x's. And there is f plus g of x. Okay? F minus g of x, same kind of deal. We're just going to subtract the two functions. So that means I'll have 5 root x minus negative 8 root x. Right? Here was my function f, here's my function g. So I got a double negative in there, so that's going to be 5 root x plus 8 root x, 13 root x. Okay? All right. So, two ways to do this. One way you could approach a problem like this, my input is now 4, not x. I could find f plus g of x like I did up here. It's going to be negative 3 root x. And then I can just plug 4 in for x. So there's nothing wrong with that. Okay, so actually, since I already did part A, honestly, that's what I would probably do. But just to show you the other way you can handle this, this would be f of 4 plus g of 4. Okay, and then I could find f of 4 and g of 4. So let's see, f of 4, that's plugging in 4 for the x there. Okay, and then g of 4, I'm plugging in 4 for the x here. And then I can start simplifying both pieces. So the square root of 4 is 2 in both terms. And I'm just using the positive root here. So then I've got 10 minus 16, which comes out to negative 6. Okay? And if we were to plug in the x value 4, then I've got... I'd have negative 3 times root 4. Well, negative 3 times 2 is negative 6. So you see you get the same solution if you found f plus g of x and then plug the 4 in. Okay? It doesn't really matter if you plug the 4 in at the beginning or the end. It's up to you. All right. Now let's find the domain of f plus g of x. Well, I already found f plus g of x. That equals this. And if I'm asked to find the domain, I need to think, do I have a fraction? I don't here, so I don't have to worry about that. But I have a radical with an even index, and when that happens, the radicand cannot equal 0. So that means x it can equal 0. It can't be negative. So it has to be either 0 or something greater than 0, right? It has to be greater or equal to 0. So that is my domain. X values can be anything greater or equal to 0. Okay? All right. Okay, next page. So now we've got some multiplication. So I've got fg of x. That means f of x times g of x. Okay, so I'm going to substitute both of those in. So f of x here is x to the third. And g of x is root x. Okay? And then I want to simplify that. You could write it like this. It wouldn't be it wouldn't be the end of the world if you left it like that. But we can actually simplify this a little bit. They're not like terms right now, but if I write them either both with rational exponents or both as radicals, then I can do something with this. Actually, it's not going to work if you put them as radicals. But what I can do is I can take this part and think of that as x to the 1/2. Right? Because my exponent is 1 and my index is 2. So now I've got x times x to the 1/2. And when I've got the same base and I'm multiplying, then I can just add my exponents together. I forgot the 3 here. Sorry. I can add my exponents together. So my exponent is going to be 3 plus 1/2. And I need a common denominator. I mean, it's going to be 3 1/2, but we usually don't use mixed fractions at this level. So 3 is the same as 6/2, right? So then I can write this as x to the 7/2. Or you could write it as the square root of x to the 7th if you wanted to put it back in radical form. Okay. All right, so that's a better version, right? It's simpler than x to the 3rd times root x. Okay, now let's find the domain of f(g) of x. So if you're going back, you can write this as a radical again, or you can just kind of think, if you actually go back to this version, it's kind of easier to look at it in that form. I can plug in anything I want for x here, but over here there's a limitation because I've got an even index here, okay? So what I'm going to think is, oh, that can't be negative, so that means x has to be greater or equal to 0, and that's going to be my domain there. Okay. Okay. And actually the same thing would happen, just to show you. If you wrote this as the square root of x to the 7th, still your radicand has to be, it can't be negative. So if x to the 7th is greater or equal to 0, and you took the 7th root of both sides, you'd end up with that same thing. Okay. All right. Moving on to the next problem. So again, we're multiplying the two functions together. Okay, f of x is 4x here, and g of x is x to the 2/3. Okay. So let's write this. I think I wanted to have division here, but oh well, that's okay. If it was division, you would just write it as a fraction and simplify it. Okay, so looking at this, I've got, you can think of this as 4 times x to the 1st times x to the 2/3, right? And that means I can combine these two pieces. So I just rewrote the 1 as 3/3 so that I'd have a common denominator here. And then I've got 4x to the 5/3. Okay, so that's a good way to simplify that. For the domain, it might help to think of this part as a radical. So if I put this back in radical form here, the 4 wouldn't go in the square root. It's just this part raised to the 5/3, right? So my index would be 3. And so this is just as simple as that version. Either of these are fine. Okay? And now my radicand, it actually can be negative because I've got an odd index. So that means I've got no limits here. My domain is going to be all real numbers. Okay. All right. So next up, a function is a relation. It's a set of points where each input value, which is usually our x, is going to have a unique output value, which is usually our y's. Okay. So what that means is you can't have one x lead to two different y's. Okay. So looking at problems like A, B, and C, and I'm trying to decide are these functions or not, I start usually by scanning the x values, and I'm seeing are there any repeat x values? And there aren't here. I've got 3, 4, 1, and 2. So whatever they lead to, I know what happens when I have a 3, it always leads to a 4. When I have a 4, it always leads to a 7. 1 always leads to 8. 2 always leads to 9. If the x's are all different, it's always going to be a function. So that one is a function, okay? Looking at this next one, I'm noticing, hey, I've got 2 different 3s. And that's not an automatic disqualification, but I want to see is that same x value leading to the same y or to 2 different y's, and it's leading to 2 different y's, okay? So think of it this way. I hit the 3 button and a 4 comes out, and then I hit the 3 button again and the 5 comes out, so it's not consistent. The 3 button leads to 2 different y values, and that means this is not a function, okay? Part C is the one that trips people up the most often, okay? Because I think what gets people on ones like this is that they'll notice, oh, there's two different 9s and there's different x's attached to them, so they'll say, no, that's not a function. But it's okay to have the same y value attached to 2 different x's. It's just not okay in reverse. It's not okay to have 2 different x values, the same x value attached to 2 different y's. So think of it this way. When I hit the 1 button, I know what I'm going to get out. I'm going to get out a 9. When I hit the 2 button, I know what I'm going to get out. I'm going to get a 9. There's no mystery what's going to happen when I hit the 3 button, the 4 button, the 1 button, or the 2 button. Yeah, and those both lead the same thing, but that's okay. As long as I know what's going to happen when I hit the 1 button, I know what's going to happen when I hit the 2 button. So this one is okay. Okay? Suppose this first one, the second one, the 2 different 3s, I don't know, am I getting a 4 out or a 5 when I hit the 3 button? Okay? Put the little arrows on here, they didn't print out. Okay, so I don't have a list of ordered pairs, but this is really a bunch of ordered pairs here, okay? And I want to think, is this a function? Well, the easiest way to do this is with a vertical line test, okay? So a vertical line test, here's a vertical line, okay? And the way this works, if I put a vertical line anywhere on this graph and it passes through the graph twice or more, then it's going to fail the test. This one, wherever I put a vertical line, anywhere I choose to put a vertical line, it's just going to have one intersection at the most. So this is going to pass the vertical line test, and it means that, yes, this is a function. Okay? On my next one, there's a bunch of different places. I could really put this just about anywhere. But hey, I've got 2 different intersections there with one vertical line. That's going to fail the vertical line test, and it means that, no, this is not a function. And it makes sense because, you know, like the point 2, 1 and the point 2, -1 are both on this graph. And so then it's going to fail because the 2 leads to 2 different y's, right? Okay. And that is it for today. See you next time.